Bismillahirrahmanirrahim. Let's go over the concept of state feedback control. It is the chapter 11. There is only two small topics in chapter 10 remaining, and I'll cover that later. But let's start the chapter 11, which is state feedback control. So, what is conventional control and what is state feedback control? Conventional control is of this form that we have some sort of a controller over here and system is over here. Uh, and we take the parameter which are to be controlled. We take the feedback of those parameters and we generate an error signal by comparison of that output parameter to be controlled with the reference value, and we uh, give that value to controller, and controller generates a signal uh, which it gives to the plant and stabilize the plant or reshape the response of the closed loop as per requirement. But this is convention control. State feedback control is different. State feedback control is that you don't measure the output parameter, but you need the this is system, and here it is output, and we measure the states of the system. What are the states of the system? States are the parameter for which the derivative of those parameters exist in the system dynamics. So for a system like F is equal to MA, which is MX double dot, and this is the states are position, and velocity, because the double derivative of velocity exists, which is acceleration over here. I can write this system in this form: x double dot is equal to F over M. And if I have interest in position and velocity both, then I'm interested in controlling the position and velocity. Then this system has two states: one is position and one is velocity. And I can write this system. This system is just a moving mass in the vacuum, in the space. So F is equal to mx double dot, right? So I can write this as x, and 1 is z1, sorry, x is z1 and x dot is z2, two states. Z1 dot is equal to z2, z2 dot is equal to f over m. Z2 dot is basically x double dot, which is f over m, force per unit mass. And I can write this system like this: z1, z2 dot is equal to 0, 1, 0, 0, z1, z2 plus 0, 1, and f over m multiplied over here, right? So, and if I'm interested in measuring the position only, then y is equal to 1, 0, and z1, z2. So this is A matrix, this is B matrix, this is C matrix. And my system is in the form z dot is equal to a z plus b u, y is equal to c of z. And these are the system states: z1 and z2, position and velocity. So state feedback control is that we measure the states rather than measuring the output. We measure the states and we feed it back, and, and we multiply the states with some constant, and we close the loop. And there is no reference signal, and we'll discuss the reference signal later. There is no reference signal. Basically, this is gone, and this is the remaining loop. So this is not an output feedback. This is the state feedback control. And the theorem is that if we have a system and we a linear system, and we can measure the states, and we implement the state feedback control, then we can place the poles of the system at any location in the complex plane, at any location in the complex plane. Uh, and this is a very strong, a big statement. Means for this kind of a system which has second order system, it has two poles. Originally, system is like this, two poles at origin, and you can calculate that by using the SI minus A inverse, which is the characteristic equation of this system, moving mass, and you'll find two poles at origin. So state feedback control allows us to place the pole anywhere, means you can place the pole over here, or if I want to make the system faster, I can place the pole deeper into the stable region. Even better, if I want to make the uh, uh, if I want to have some oscillatory response, uh,